Hey, welcome to trig functions in the unit circle. You might not know what that is, the unit circle, but I'm going to pose some questions for you so you know about trig functions. That's all this stuff here. In a right angled triangle, you've learnt something about, I think, SOHCAHTOA. Probably remember that. Hope so. But SOHCAHTOA is the sine of an angle is the opposite divided by the hypotenuse. The cosine is the adjacent divided by the hypotenuse, and the tan is the opposite over adjacent. And for any angle, any given angle, those ratios of the possible sides around it are constant values, characteristic of the angle, like a fingerprint for the angle. You know all this stuff. But over here, you see half of a protractor measuring angles, and you can actually get angles, of course, bigger than 90. Okay, so that the angle here, let's take 120 from there around to there, that angle is 120. Did you ever wonder, can you find the sine of 120? Could you find the cosine of 120? And could you find the tan of 120? Would they make sense? Think for a minute. Try to think. Try not to get a headache also. Think though. No. Ever wondered? Yeah, maybe. But no, I don't think that's possible, is it? Because you can't fit 120 degrees in a right angled triangle. If you draw a right angled triangle, what's left? Some angles of a triangle are 180. So that one and that one together have to add up to 90. So in a right angle triangle, when you're doing all this SOHCAHTOA stuff, a 120 degree angle won't fit. So it shouldn't be possible. No, it should not be possible to do that. But hang on. Hey, you watch this now. Come down here. Uh-oh. What did I do on the calculator? I put in sine of 120, cos of 120, and I got numbers. Hey, what's going on there? Well, that's the secret. Trig functions and the unit circle. All of a sudden, your trigonometry explodes. And why are we going to work with a unit circle? Well, because there are some things that follow a cyclic pattern, like a Ferris wheel. You hope it follows a circle, otherwise you might get stuck at the top. Not good news, mate. And what else follows a circular pattern, if you like, a cycle? Temperatures, tides, go up and down. Follow a cycle. Maybe we've got to look at that sort of behaviour in defining some behaviours around a circle. So I've got this for you here. We're going to make up what's called a unit circle. A unit circle has radius 1 unit. Radius is 1 unit in whatever units you want. Could be centimetres, meters, or whatever. So this is 1 here. And all the radii are 1. See that all around there. We've got a Cartesian coordinate set of axes there as well. But look at what I've done. Got a little blue triangle drawn in there. And it's a right angle triangle. And what do you notice? Well, if you call this angle theta and it's got a point on the circumference, it's got an x and y coordinate, what do you notice here? Let's just tidy this up a bit. The side down here would be the x movement to get to point y, and the side here is the y movement to get to point y. Okay, so let's pull that triangle out and have a closer look at it. What do we notice? Well, this is 1, that's theta, this is x, and this is y. So in that unit circle, if we looked at the sine of theta in this triangle, it'd be the opposite over the hypotenuse. Well, that just come to y, because the hypotenuse is 1, because it's a unit circle. And the cos of theta would be x over 1, that'd be x. Now that's neat. So if you have an angle here and a point on the circumference of the unit circle, the y coordinate is the sine and the x coordinate is the cosine. What's the tan? Well, the tan of theta is opposite over adjacent. so it's y over x. Or, as you know before, from right angles, it's the sine of theta divided by the cos of theta. Well, that's interesting. But you haven't seen it yet, have you? Have you got the connection yet? If you went around to 120, which is about here somewhere, could you use that new definition? Because here would be your point now. Let's call this point Q, and it would have an x and a y. So here's a new definition. Based on extending this right angle triangle, hang on, we just got to stop that there for a minute. Sorry about that little glitch there. So if we extend that, we could say the sine of this angle here, okay, call it phi, the sine of phi, keeping this new definition, would be this y up here. It would have its y. The cos of phi would be this x here. And the tan of that phi, which could be 120 degrees now, could be bigger than 90, couldn't it, would be y over x. So it opens up a whole new realm here. If you define this on the unit circle and carry it into the next quadrant, then you can have angles bigger than 90. Angles can be greater than 90. So you're going to keep going. This is called the circular function definition. Here, circular functions, sine, cos and tan, go beyond 90. So it's still trigonometry. You're measuring triangles. Couldn't go beyond 180 in our course here because we're just going to be working with triangles. But in other mathematics, you can actually go right round and have sine, cos and tan of angles in this quadrant, like what, 220, and in this quadrant 280 or something. You can actually extend this definition to here, where the sine and cosine are the y and the x in that order, right, because the y is the opposite here. So the y is the sine and the x is the adjacent, cosine. Using this idea of circular functions defined on the unit circle. This becomes very useful in motion problems, in physics. It becomes very useful in anything with a circle, like a Ferris wheel, or with functions that reproduce in a cyclic pattern the same behaviours, like temperature and tides and so on. Okay, let's come down and define some of this now. Here it is here. Oops, hang on, we'll just go back up again here. Okay, here we are. Alright, we want to go to here, I think. Okay, so the x-coordinate of P, any point P moving around the unit circle, is the cosine, and the y-coordinate is the sine. And you can see cosine must be between -1 and 1, and so must sine, because we're now on a unit circle, and there's the maximum value of the x, and here's the minimum value of the x. That's 1, or 1 unit radius. That's the maximum value of y. This is the minimum value of y, or radius of 1. So we could summarise it with this diagram. There, the x-coordinate is the cos, the y-coordinate is the sine, with the angle just going round and round. Okay, new enlarged definition of sine, cos and tan based on the unit circle, so they're called circular functions now. Okay, so let's have a look at this. Now when we move around the circle, interesting enough, the positive direction is anti-clockwise. And if we go down this way, it's negative direction. Now we won't be working in this course with the bottom quadrants there, because we're only working with triangles, and triangles, of course, some of triangles may not have a 90 in it, but these add up to 180, so no angle is going to go past here. That's going to be the total in the triangle, 180 degrees. So we don't have to worry about these two quadrants here. So this one is an enlarged definition. You can think of it as 180 plus 32, 10, or neg 150. We won't be doing that in our course here now. Okay. The interesting thing, I think, if you are working in this top quadrant, top two quadrants, sorry, then what we can say is both x and y are positive there in that quadrant, so sine and cos are both positive, and then in this quadrant the x has gone negative, hasn't it? Negative x. So sine is still positive, that's the y value, sine is positive, but cosine is negative. So you get different patterns of pluses and minuses as you go around the quadrant. So we'll only be looking at those that relate to a triangle where the angles must be less than 180. So let's have a look now. Alright, so here's our protractor again, and obviously here you can get any size angles. Now we're going to use this diagram in a minute to estimate the sine, for example, of 10 degrees. What is that? That's the y coordinate. So we want to estimate that value there on this scale. So this scale is 1 unit, so it's 0.5 to there. So we will estimate this at just under 0.2, I think, there. We can estimate that as just under 0.2. And we could work out its cosine, which is the x-coordinate, and it's getting very, very close to 1 here. You'd have to actually measure down there. The x-coordinate would be that. Okay, so estimating those values. Alright, so let's have a look at some exercises here from Hayes and Harris publications here. So this is just 1B1. That's the only exercise we need to do in this particular course. So there are, how many problems there? Let's have a look, bring it down a bit. I think it might be a 9th one. No, we'll come down there in a minute. So I want you to use the diagram to answer some of these questions here and see what you think. Alright, so working from 0 to 180 in triangles. Let's go on and look at the last question here, and then we'll look at the answers. So not much work in this little presentation, just a new idea and an idea of why we've done it and applying mathematics to practical situations. Alright, I'll give you a look at the answers now. We come down for the answers. There are the answers. See if you got those. You won't get the exact. This is a little bit too exact here probably. Hard to read that off, but see what you think and get the idea of it. Alright, I hope you've enjoyed that. That will help us later on when we're going to be doing something called the sine and cosine rules. The idea that you can actually find the sine, cos and tan of an angle bigger than 90 degrees with our new circular functions definition. I hope you enjoyed that. I'll catch you in a later presentation. Cheers for now.